All right, hey folks, by popular demand, I'm going to be giving a quick introduction of the CP3. I'm aiming for about half an hour. I'm going to try to go through most of the code line by line, but we'll see how it goes. This is for MIT's 2155, 2156 course, fall 24. And yeah, I'm just going to kind of walk through the starter notebook, explain the data, explain the starter code we've given, and then talk about the utilities after that for just a little bit. All right, so the premise here is that, and by the way, I've run this notebook already, so things should go pretty quick, but I'll tinker around, show some things, run some cells over again, and try to build some intuition. Okay, so the premise is that you've been hired as an AI engineer to basically help accelerate the prototyping pipeline for a bike company. And the idea is that they're going to give you these rough, incomplete design concepts, and your job is to visualize the completed design concept. So they'll give you a partial image, a text description, or like a marketing pitch, some parameters for what they want to see in the final design, and then you're going to say, okay, here's what the final design is going to look like. So that's the AI predictive modeling task. Now, the first thing that we do is give you this utilities function to load the data. So this load data function will give you 5 things. The first thing, or the last thing here, is this targets. This is the final complete images that you're trying to predict. And these first 4 things are what you're going to use to make that prediction. So this is going to consist of partial images. These are the images with some components, like parts of it, whited out. The masks, these tell you where the whited out areas are. Parametric information, this is just a vector of numbers. And then description, this is a string text description. This is the shape of these different components here, so we can see the partial images. For all of these, we've got 10,000 of them. So the first dimension of all these things is 10,000, sorry. And they are like ordered, right? So the first one of all of them corresponds across, right? So these have the same order. All right, so the partial images, the shape of them is going to be 3 by 80 by 128. We've got, again, 10,000 of them. And what this is 3 color channels RGB, height 80, width 128. The masks, this is going to be 4 values saying what are the left, bottom, right, and top boundaries of the mask for each image. Parametric data, this is 96 variables, basically just numbers. You get, this is a list of strings, so for each one you get a string. And then the target images, this is the same shape as the masked images, basically. These are the ones that you're trying to predict, right? Okay, so we can take a look at some of this data here. So the parametric data, if we look at the first one, we can see about half of them are nans. This is by design. The company is only giving you, they've only decided on half of the parameters, so the other ones are kind of up in the air. And for every single design, the nans are going to be different. So it's kind of on you to infer what the different parameters mean and to try to deal with that incomplete information as best you can. We can also take a look at what the partial images look like. So partial images, yeah, it's mainly, I mean, it's pixel intensity values between 0 and 255. We can see like np.max of this. So max value is 255, I think. And then min is going to be something close to 0.5. Yeah, so this is the minimum for this first image. But if we look at the second one, this minimum will probably be different. Yeah, so this one, minimum is 0. We can also look at a histogram. So I'll quickly try to do a histogram here. Right, so we can see that for the first image, we've got, yeah, most of them are white pixels over here. Actually, maybe let me just look at the red color channel here. So let's say 0, 0. Most of these have no red, basically, but we can see that there's some variability here. Now, also, if I take targets here, the partial images is basically the targets with some parts whited out. So we expect a little bit more white. Before I ran this was, so 8,000 in the partial. We would expect a little bit less white in this one. Yeah, so this goes down to like 6,700 or something. So a little bit less white in the completed image because there are not those whited out regions. All right, anyways, I think I've lingered on this a little too much. So masks, we can take a look at the masks. These are just 4 values, basically. I'll explain this in a sec. I think that's everything. And then, description. Description 0, just a string. Okay. So we've made a little function here to compare some of the data here. So in this one, the warm blue comet impact comes with dual bottle mounts in the C-tube and down tube, designed for effortless water access, a natural bamboo frame, an advanced belt drive setup, sleek, ultra-efficient composite wheels, urban trackball horns, and a set of aerodynamic bars to take your cycling further. Okay, so it's like cute little marketing pitch, right? And really what it is kind of like a list of features. So this tells you a lot of information about what is in the design. We can also, run this again. There's a lot of different things. So, in this case here, this is a good example. Like, it says, with a sturdy rear rack for carrying gear. If you hadn't seen that in a text prompt, given this masked image, you would have no idea if this bike has a rack or not. But given that you've been told in the marketing pitch that it has a gear rack, now you can figure out, there's supposed to be a gear rack. So if you were trying to just infer what this design looks like based on the masked image, oftentimes there's like a lot of correct answers, right? There's a lot of like different ways that this bike can look. So essentially you have to guess if you're just using this masked image, but ideally with the text and maybe the parametric data as well, you can make maybe I'll say a more informed guess. But with the starter code, we're just going to be making predictions based on the masked images, and it'll kind of be on you to incorporate the parametric or the text, which should improve performance. All right, so real quick, this is what the masks look like. So this is like the left, bottom, right, and top boundary. So for this first one here, this is like the one over here. So this is 0. So this is the left side of the mask is actually at the 0th like index here. Bottom is at 50. We count from the top to the bottom when we do an im show. So this is like 50 from the top. Next is 70. This is 70 from the left, and then 17 from the top. So that tells you basically the bounding box of this mask. And you can look at the other ones as well. So this one, like 1 from the left, you can see there's like 1 pixel there. Okay, so that's what the mask looks like. That just tells you where the box is. All right, so starter code. Again, this is just going to try to predict the final image based on the partial image. We do some imports, check if you have a GPU or not, and then we have some helper functions here. This one I'll explain in a sec. This one is scaling the images. Again, natural scale is like RGB between 0 and 255. So to make it easier, we'll scale it from 0 to 1, and then this next function reverses that scaling. All right, so first we're going to scale the images. Then so this is both the partial images and the targets. We scale both of them. Then we do this masking. So we're going to, what this does basically here, I'll just print out what this looks like. So mask channel, mask channel.shape. So the shape of this guy is 10,000 by 1 by 80 by 128. Basically what this is doing, and I should probably just do plot.imshow of this first one here. Yeah, so it's just a black and white that shows you where the box is, right? So this is an extra channel that we're appending onto the partial images. So we're going to have RGB mask. So this is what we're going to feed into our model. You can see it's shape 10,000 by 4 by 80 by 128. This line here is where we actually do the concatenation. And then what we're trying to predict, this is largely unchanged except we've scaled it. So, we can processed targets. If we look at this is going to be, between 0 and 1. I mean, most of these are white, so it's 1s. Okay. So, right, that's what we got. And then, so we're going to convert these to tensors. Then we do a train test split. We can take a look at the shape of these things. So train masked dot shape. This guy should be, oops, what happened? I think I ran extra cell. 9,000 because we were setting aside 10% for validation. So our training data is going to be 9,000. Our validation, validation is going to be 1,000. And then, okay, so then we move them both to our device, whatever device we're using, in my case, GPU. Then we construct a data set out of it. I can get rid of this. And then over here is where we set up the VAE. So if you're not super interested in the architecture, you can skip forward. I'm going to try to go through pretty close to line by line just to explain what everything's doing. So over here, we're initiating things. We just set up what all these pooling convolution stuff are defined, and then later we're going to call these in the forward pass. But basically, we're going to define all these convolution layers, define this pooling, and we start out with our first convolution with 4 input channels. As we said, we have RGB and mask, and then we're going to gradually increase this each time we go. The way that we have the kernel size and stride and padding set up, these convolutions actually don't change the image dimensions, but this pooling does. So each time we do a convolution here, let's say conv1, we're going to call a relu after that. So that's our activation function, and then we're going to do pooling. So if our input is 4 by 80 by 128, this first convolution will not change the 80 and the 128, but it'll map it into 8 channels, because we said 8 output channels. So the output of this here is going to be 8 by 80 by 128, and this pooling is going to apply to the 80 and the 128. So then the output of this pooling will be 8 by 40 by 64, right? So this is shrinking. I mean, we said the kernel size is 2, stride is 2. So this is basically just going to cut down our dimensionality by 2. So each time we do a convolution and pooling, we're shrinking the dimensionality by 2. So at the end of the day, we've gone from 80 by 128 down to, let's see, 5 by 8. And we've gradually increased the number of output channels. So at the end of this, we have 64 output channels. This will be a 64 by 5 by 128 output. Okay, so this is the convolution and pooling here. And then basically we are going to do flatten this, and then we're going to call a fully connected layer on this. So this fully connected layer, you can see we've defined it here. The input size is going to be 64 times 5 times 8, whatever that ends up being, 250, I don't know, 2560, I think. And then 128 is the output here. And then this FC2 is going to, oh, no, this is the decoder here, sorry. So FC1 gets passed to a ReLU. And then what's interesting here is that in the encoder of a VAE, we actually need 2 outputs. So we need to output a mean and a variance. So we're going to have these 2 fully connected layers that instead of going sequential, they're going to be kind of in parallel. So X is the output of all that stuff before. We're going to call FC mean on this and FC var on this and return both of these outputs. Okay? All right, so decoder, very similar structure to the encoder, but kind of in reverse. Instead of convolution and pooling, we're going to do convolution transpose. And the way that we have these all set up is that this will basically double the dimensionality each time. So once again, we're going to start with a 64 by 5 by 8 thing. We have 2 linear layers. First goes from latent dimension to 128, and then 128 to whatever this thing was. I forgot what I said. And then, don't want to do the math again. Basically, you reshape this output, which is just a vector, into a 3D thing, and then all of these convolution transposes get applied in sequence, each time bumping up these dimensionalities. We basically have these cascading, so you have fewer and fewer filters. At the end of this, this will be 3 channels in the output, and then it'll be 5 times 1, 2, 3, 4, 2 to the 4th, 16, so 80. 8 times 16 is 128. And then at the end, this comment's a little bit confusing. So the sigmoid is not here. We call the sigmoid down here, but I don't really know why we did that. Basically, we need to just map this output between 0 and 1 because that's what we're trying to predict. We're just making it easier for our model. We know all the outputs are between 0 and 1, so we put sigmoid over here. Except we don't put it there, we put it below. It's the same thing. Anyways, so now we define the VAE class, right? So we define the decoder and the encoder class. So now we define our VAE. We say our encoder network is our encoder class. Decoder network is an instance of our decoder class. We set the latent dimension here. And then we have this function reparameterize, which is kind of just part of a VAE. What this is doing is it is basically doing a resampling. So our encoder will give us mu and log var, and given mu and log var, we're going to resample those. So mu is the mean, log var is the log variance of a normal distribution. We're going to say, okay, we're going to resample new point from that normal distribution. So this rand n is doing random selection from a standard normal distribution. That's epsilon. Epsilon gets multiplied by our standard deviation, then we add mu. So this is basically sampling from the normal distribution defined by mu and log var, right? So that's what reparameterize does. Encode, this just calls our encoder and then does this reparameterization step. That's all. So this basically takes in x, which is our starting masked image, and eventually goes to z, which is our latent. And then it returns z, mu, and log var. Decode is going to take in x. In practice, this is actually z. We probably should have called it z so it's less confusing. It's taking in a latent, basically, and it's calling the decoder network on this latent, and then applying sigmoid. So we didn't put the sigmoid there. For some reason, we put it here. Whatever. So it calls the decoder, calls sigmoid, And then the forward pass is going to do all of this together. So we get the encoder, we get z mu log var, and then we get decoder, and we get output. We return output mu and log var. Okay. And then I'm going to skip this for a sec, talk about this VAE loss. This VAE loss uses, well, okay, let's just quickly talk about the summary. So this function just shows like model summaries. I don't think you really need to read into it too much. Then this VAE loss, this is what's calculated in the actual training loss. There's two components. One of them is reconstruction. We call it reconstruction, which is probably a misnomer here because normally when you train a VAE, your input and output data are the same. You're trying to reconstruct the exact input data. In our case, we're passing in a masked image with some parts whited out and trying to predict what the actual image was. So in a sense, it's not really reconstruction anymore, but the reconstruction loss idea holds true. It's just like how close did we get to whatever we're trying to predict. So in this case, we use MSE. This is just mean squared error. How close did we get to this final target image that we were trying to predict, right? So X in this case is the target image. Recon X is like what we reconstructed. Again, it's not exactly reconstruction, but it's what we predicted. This KL divergence here, this is a little bit challenging to explain. I would kind of look into some of the theory for VAEs to exactly understand this, but basically this is looking at how similar our distribution defined by mu and log var is to a standard normal distribution. So it's looking at the KL divergence between this probability distribution defined by mu and log var and what we want to sort of normalize it to, which is a normal distribution. And what this does is it basically makes our latent space organized and predictable so that if we sample a random vector in our latent space, it'll ideally decode into a realistic design, or a realistic bike frame in our case. So this is what basically makes an autoencoder into a variational autoencoder, where the variational autoencoder is a generative model, so it can generate new samples. That's what this KL divergence does. It makes sure that the latent space is organized and that we can actually do random sampling there in a generative setting. Now, this weight here, this basically modulates the KL divergence, and if we set this to 0, this would turn into a normal autoencoder, and this kind of modulates. If we set this very low, the reconstruction would be very strong, but, if you did a random sampling in a generative setting, it'd probably be kind of bad. So this kind of modulates the generalizability of the VAE. If we set it very high, it would be more generalizable, but the reconstruction would probably be not as good. So this is something that you kind of have to play with, and depending on your problem, this weight needs to change quite significantly. So that's just one of those hyperparameters you have to be aware of. All right, so model training here. We take in a data loader or model optimizer, how many epochs and device. There's a lot of stuff here you don't really need to pay attention to. It's like, calculating the running loss, like moving average and stuff, and then displaying progress bars and stuff like that. I think the interesting thing here is, all right, so we're going to loop over however many training epochs we're going to do. This here is wrapping like our data loader in a progress bar. It's a little bit convoluted, but at the end of the day, we're getting like batches of data from our data loader. And what we get is data and target, data being our masked images with the mask channel appended to it, so RGB mask. And then the target, these are our just our normal complete images that we're trying to predict. Move them both to the device. Over here, we're gonna zero the gradients of our optimizer, just get everything set up. We're gonna call the model on the data. So again, model here, because this is a PyTorch neural network module here, what basically calling model does is calling this forward function. And the forward function calls encoder and decoder, encode and decode, which call the encoder and decoder respectively. And that gives us output mu and log var, calculate VAE loss based on the output, the target that we're trying to reconstruct, mu and log var. And then this is our final loss. Backward basically calculates the gradients with respect to our model parameters. And then the optimizer will update the weights of the model. Okay. Yeah, and then we do some stuff like, track the loss, just put it into the progress bar so we can see how it's doing and so forth, blah, blah, blah. Pred image, I don't think we actually use this function. I can get rid of this. Anyways. Okay. I'll probably update the GitHub and get rid of that function. I don't think we use it anymore. Okay, so here we're going to, all right, we make an instance of our VAE, right, latent dimension 128. And then we show summaries given our input size of 480, 128. I think we gotta hit scrollable here. Okay, so this is kind of long. This is the encoder. You can see the structure. We've got 385K parameters. The decoder here, we've got 371K. So basically the same size encoder and decoder. And this makes sense because they basically just have like a mirrored structure. So it's kind of the same thing. Okay. So that's what our encoder and decoder look like. Here's where we train. This is the learning rate. This is the optimizer here. We pick Atom W. We can pick some other optimizer. Atom's the normal one. And then we train it for 200 epochs. And again, we can track all the losses and stuff. This took about 5 minutes on my computer. Might take more, might take less, depending on what hardware you have. And then we have this function to actually combine the predictions with the original masked images, right? So in our masked images, most of it is unmasked stuff where we actually know what the bike looks like. And then we're going to make this prediction. Instead of just submitting the entire prediction, why don't we just take the prediction in the components that we don't know, right? So we're going to combine the areas that we do know from the masked images with the prediction in the area we don't know, right? So this is what the combined org and pred does. Over here, we just we separate the validation data. Like again, we like added this mask channel, right? So this just separates into the image itself and the mask. Then we pass in the whole 4-channel thing into the model, get the reconstructed images here. The reconstructed images, again, this is like the validation data, right? So we're trying to evaluate how we did on the validation. We turn it into a NumPy array. Then we call this combine org and pred. So what's going in here is the reconstructed images. So these are basically our predictions. The original masked images. So this is like the images with some stuff whited out. And then the mask information. So that's why we had to separate these guys here. It's to pass them into this function here. And then these combined reconstructed images. This is the combination of our predictions with the actual regions that we do know, right? And then this is, we need to convert it back to RGB. This function just scales it back from 0 to 255. And then the image ground truth, we also scale this from 0 to 255 because we scaled that before. All right, so these are our predictions and these are the ground truth, okay? So now we have a little function that's in the utilities to compare the predictions with the ground truth. As you might guess, on the left here, this is our predictions, and on the right, or in the center, this is our ground truth. We also have this little thing to visualize the residuals, or the error. So you can see, anywhere that's not in the mask, our predictions are spot on because we're using the actual original data that we know, right? So there is no error in these regions, but obviously where we're making these predictions, there's plenty of error. Now, I think what's interesting to note here, so, at first glance, these predictions look pretty bad, but if you look at some regions like the wheels, for example, like in this one, it sees that this is a disc wheel, and it's very easy to predict what the rest of this wheel looks like. So it's actually doing pretty well when it sees some features and it can reasonably predict what the rest of the feature looks like, right? I mean, this tri-spoke wheel, I think it's done a pretty good job here. This one is like, okay, it sees just the very bottom of what ends up being a wheel with 5 spokes. So it's probably difficult for it to gauge if this is supposed to be 5 or 4. It kind of guesses that this is 4. But you can see, like, in most cases, when it sees most of a component, it can make a pretty good guess. But when it comes to, like, the bike frame, like, there's a lot of different shapes of frame that it can take. And for it to understand exactly the angle of these components, it's got to look at such a small little area. So it's very difficult for it to figure a lot of this stuff out, especially when there's many different realistic cases for what the bike might actually look like. So this is kind of where, you got to use the parametric or the text information to actually figure out what this looks like. Otherwise, your model is randomly guessing and, you can't really expect to get this right, right? With that said, there's plenty of room for improvement. I mean, there's plenty of areas where, like, for example, the color. You can see the color here, and, maybe it should guess, like, a little pink cloud rather than a gray cloud, right? Why is it? It knows the frame should be pink, or, it should know that. We know that. So, there is room for improvement. We can also visualize some other ones here. Maybe we can see if we find anything interesting. In most cases, it's really struggling with the frame, but in general, it gets the wheels pretty good. This is an interesting case where most of the wheel is covered, so it doesn't actually know what type of wheel it is. In this case, it basically has to guess, because there's no way of it knowing whether it's like a tri-spoke wheel or a normal spoked wheel or a disc wheel or whatever. But in this case, it's kind of guessed correctly that it's a tri-spoke wheel. Yeah, so you get the idea. There's room for improvement. And you can also see there's like a lot of weird bike designs, right? So some of these have like overlapping components. That's part of the challenge. Okay, so, all right. I have a little bit of discussion here. It's kind of what I mentioned. All right, so this is the scoring. The scoring here is a combination of something called structural similarity index metric and mean absolute error. Basically, at the end of the day, the more similar your prediction is to the target, the higher the score is going to be. Maximum is 1. Minimum is technically 0, I think, but if you did like random noise and submitted that would probably get you somewhere around a 0.5. So, yeah. This is this VAE solution gets 0.952. We can also look at the distribution of scores across the 1,000 in the val set. So you can see most of these are around 0.95, something like that. Now, I also thought it'd be interesting to take a look at the scores if, for example, we hadn't merged our predictions with a non-master region. So what if we just took the entire output of the VAE and submitted that, even the regions where we know the actual ground truth, but we just submitted our reconstruction anyways. That gets us 0.91, so that's significantly worse. So combining the predictions with the areas that we know actually significantly improves the score, as we can see. And then also, interestingly, if we just submit like the empty white boxes, right? So if we just submit the masked images as our final predictions, that gets us 0.903. So this is kind of like the bare minimum. This is if you literally just submitted the partial images as the complete images, that gets you 0.903. Okay, so these are some reference points just so you know what generally does a baseline score look like. Hopefully we can see some scores above 0.952, and then if you ever get a score below 0.903, that's probably a bad sign. That means you could have literally just guessed a white box and it would have done better. All right, so hopefully that gives you a little intuition. You can also dig into the actual functions and the utils if you'd like. All right, so how to improve from here? So I think one thing that the teaching staff has thought about is changing the type of model you use. So one of them is using a more powerful generative model, like a diffusion model, or some kind of non-generative forward model, such as a UNet. So for the diffusion model, our current plan right now is to give you a starter diffusion model, basically as demo 9. So that should hopefully get you started if you want, and literally will give you diffusion model applied to this challenge problem. So it should be just good to take and run with if you want to start with the diffusion model instead of this VAE. And then there's also the option to use a non-generative model. So technically you don't need a generative model. You can just have a deterministic forward model to predict what the completed image should look like. The main benefit of the generative model is that you can generate many different variations for what the image could look like, and then maybe you can subselect, like pick the best one based on the text matching or something like that. So I think there are benefits for using the generative model and using its capability to generate many options, but you don't have to. You can use a deterministic forward model as well, such as a UNet. A UNet is very good for this kind of thing. Okay, so that's one option. Another one is that you can actually create more masked images. So we've given you 10,000 targeted images and 10,000 masked images, but we give you the masking function. So you can take these 10,000 for each of these. You can create 1,000 masked images with masks in different places and sizes and shapes. So you can essentially create a bunch of synthetic data. At the end of the day, you only have 10,000 targeted images, so you probably get diminishing returns at some point, but you can create a lot of synthetic masked image data if you'd like. And then I think finally the big one that we're hoping you consider is to look at the parametric or the text information, because as I mentioned, in a lot of cases you just do not have enough information to make a strong guess as to what's going on inside that masked box without looking at some extra info. So I think oftentimes the text info can tell you if there's a cargo rack in there, what type of wheel it is, all this stuff. You just have to figure out a way to process it. And then the parametric info, if you can train some kind of model, those parametric information can oftentimes tell you like what the shape of the frame looks like, a lot of stuff like that, and also what components in there. Again, it's not labeled, so you sort of have to figure out what each of the parameters means, or just don't throw data at it, and hope for the best. But yeah, I think the main strategy to improve your model beyond random guessing is to use the text and the parametric data. So to use the parametric data, you have to deal with all those NaN values. A basic strategy, you can perform imputation. So basically just, for column 1, if it's a NaN in this design, just take the average value of all the other ones where it's not a NaN and put that in. So that's just some kind of basic imputation approach. I think it should be like a one-liner from scikit-learn. There's existing methods to do this. For a more advanced strategy, you can also just feed in the NaNs and basically mask them out in your training, and basically you don't calculate the loss over the masked regions. That's another option. That's a little bit more advanced. So there's a lot of ways of dealing with the partial parametric data, and I think some of them are very approachable. For the text, I think a simple approach can be using some kind of word frequency-based, what we might call like a bag of words approach. That's just looking at how frequently, did these words appear in this prompt, and then that can basically be a vector representation for your text. So it just counts the frequency of certain keywords. I think for a more advanced approach, you can take some pre-trained language model, so maybe a text embedding model, which will map each text string into a parametric vector that ideally captures the key, semantic meaning of that sentence. So, you can use like universal sentence encoder, you can use a BERT model, you can use some kind of larger language model as well. There's a lot of options, and right now the current plan is we'll give a quick introduction to that in demo 10, but we'll see. And then once you have a vector representation of your parametric data, or your text representation, you can put it into your model somehow. So demo 6, we showed you how to create hybrid neural networks. You can use something based on that. There's a lot of ways to go about it. All right, so finally, preparing your submission. So at this point, you've trained some model to make a prediction using the masked images, the masks, the parametric data, and the descriptions. Now you basically need to make the final prediction for the test set. So we have this utils function here, load data if you specify test. That'll give you the test data. Obviously, we don't give you the target images, otherwise you would know the answers. But we give you everything else for the test set. You basically make your predictions here. So, okay, we need to scale the images, get the mask channel, concatenate it, turn it into a tensor, pass it into our model. These are our predictions now, and we're going to say, okay, now we convert it to RGB. This is our final submission. Okay, so these are predictions for what would be like target test or whatever we call it. And we have a function to validate the submission, make sure it's in the right format and everything, and then generate a random ID, and then save it as whatever, this NumPy file. We'll have a form just like in CP2. You can upload it. It'll be a live scoreboard. And this time we'll give you only 10 submissions total per person. So make sure you use them wisely. But in this case, I think your validation scores here will be very, very similar to your test scores. So I don't think you need to submit to the scoreboard to evaluate on the test set every single time you make a small change. The validation score should be pretty accurate. Okay? All right, so real quick, I'll also go through the utils file. First, we've got the data loading file. Don't really care too much about this. We've split the data into several batches just so it goes up on GitHub without a problem. But yeah, just loads the data. This stuff here, so these next 3 functions here, this is stuff related to the scoring. So if you're super curious about our evaluation metrics, you want to dig into it, you can take a look at these functions. Basically, it's just a weighted combination of MAE of the residual and this SSIM metric. Okay, this is just a helper function to do this plotting from, this guy over here from the starter notebook. You can obviously use this function, modify it if you'd like. Apply random mask, this is important to know. So if you want to create more synthetic data, this is the function that creates the masked version of the image data. So, and we use these exact parameters, 0.4 and 0.8. So if you want to create more masked image data, you just run this function, basically. This was the function used to mask the parametric data. I don't expect as many people to use this necessarily, but it could be interesting to reference. And technically, you can create some hyper masked parametric data, if you want to mask even more of the parametric data, you can do that. So that could be useful for training certain types of models for certain solutions. Okay, this generates the random ID, whatever. And then this one validates your submission, just checks the shape, checks the data type. And then if it looks like your submission's improperly scaled, we'll give you a little bit of a warning here, but you probably want to just check this yourself. Make sure that you've remembered to scale it between 0 and 255. Okay. All right, I think that's it. So let me just make sure I've gone through everything. Yeah, all right, I think that should be everything. So if you have any other questions, you can shoot us a message or stop by office hours. Hopefully this was helpful. If it was, I'll try to keep doing this for demos and so forth. And thank you again to the person who suggested this. Yeah, looking forward to seeing what you all come up with for the challenge problem. Thanks. Have a good one, folks.